Hello, this is Argonne at Lunch. My name is Justin Bro, and thank you for joining us today. I'm here at Argonne National Laboratory, which is one of 17 Department of Energy national laboratories. Argonne, in particular, focuses on energy and environment, national security, and a whole lot of supercomputing is going on. But today we're going to be talking about modeling. How do scientists create the models that go into the things that we know about? Today we're going to be talking with Doug Sesterson, who is a research meteorologist here at Argonne National Laboratory, as well as Rob Jacob, who is a computational computer scientist. Now let's go, and Doug is over here, so let's just start with Doug here. Good morning, Doug. How are we doing today?
Good morning. Doing fine, thank you.
All right. So why don't you tell me my first question for you is, what type of researcher are you?
Okay, so in my mind, there are different kinds of research scientists. There's theoretical, and these are the people that you can't do an experiment at the beginning of the universe that you don't have data for. So most of the science is done there is through logic and the physical laws of nature. Then there's what I call the observationists, and I put myself in that category, that, gee, we want to go learn something, and we can see it, and so we can take data. And then as we get the data, we can start to understand how it works. And there's a third type, and I call that the modeling or the data visualization type. In other words, sometimes you can't put something in a lab and study it. It's too big. So we come up with what we call analogs for things that are too big to put on a bench in a lab. So that's what we're talking about today.
So you are clearly an observational, so you put yourself in that camp. But tell me a little bit more about what a research meteorologist does, because I understand that's what you are.
Okay, true. Well, I went to school, college, and I thought I was going to be a physics major. And after about 3 years of that, I thought maybe I would like to do something a little bit more exciting. And we were moving our physics lab that summer, and all of a sudden this skies go blue-green, and sirens go off, and we get hail the size of eggs, and windows are breaking, and people are screaming, and I'm sitting going, what's this? And they said, well, that's weather. It's meteorology. What do you got to do to learn all this? Study weather, study meteorology, and off to graduate school I went, and the rest is history.
There you go. Inspiration by near annihilation by a major storm with hail the size of eggs. I understand that. So my next question for you is, what we're doing is we're modeling. So as an observationalist, you're going out and you're seeing things and you're trying to create a model of it. Talk to me a little bit about data quality and how that applies to the work that you do.
Well, data quality, today I'm mostly involved in climate research, climate science. So one of the things that we're most concerned about when we take observations for a long period of time, that as technology comes along, we get newer and better improved instruments. And so as we replace them with better units that give us more detail and so forth, we want to make sure that we don't disturb the long time series trend by arbitrarily adding something that has a bias to it. So we overlap those instruments for a period of time, maybe a year, sometimes longer, to make sure that we understand if we're going to take this one out and plug this one in, that we don't disrupt the longer-term time series.
And one here, I know this is a softball one for you. So tell me what the difference between climate and weather is.
Okay, the short answer is that climate is what you expect, and weather is what you get.
Did you hear that?
So what that really means is that we'll take a 30-year average of climate. So if we put a weather station outside of Argonne and we measured every day the rainfall, we did that for 30 years and we'd average it, and we would look over 30 years what would be the weekly average or the annual average or the daily average. When did it fall? And we get to build a nice distribution of data. That's our expectation over 30 years of what it would be like. It's an average. But the weather is actually what we get. We know that the average weather doesn't occur every day.
It goes high and low.
Goes high and low. So when you're watching the 10 o'clock news and they say the normal for today is like 62 degrees and it's going to be 72, we're above average. So the climate, what we expect year to year, would be 62, but what we got today was 72.
And it is a beautiful day in Chicago. If you're not here, sorry, maybe next time. All right, so my next question is going to get to this cool demonstration that we've already promoted for you. So Doug is going to do a demonstration of how do we model a tornado. So why don't we walk over to our area over here. So tell me how, and you're going to be doing all explaining here, so you tell me how you model that.
So actually, it's a pretty simple device. I'm going to shout out to my daughter, Rachel Hopper. She did this as an 8th grade science fair program and at Homer Glen Junior High. And the idea was to build a tornado chamber and then ask it some questions. Create a tornado. So this is basically plexiglass. You can buy that at Home Depot. And it's got clothespins in on the side to keep the flow open. It's got a ceiling fan. Okay.
Let's see if we can get Doug a little bit closer so we can get some close-up shots there.
So the idea is with the ceiling fan, when I turn it on right now, the air is being drawn out of the box but it's being replaced by the air coming in through the box through the four sides that are open. So if you can imagine, the wind column is going like this. And so it gets into the middle, it says, what do I do? Well, the strongest force of whichever leg has got a higher wall that's open, a larger opening, will actually cause wind shear. It'll cause it to rotate, start to turn. And so we can simulate then, that's what we think tornadoes do, it's a rotating column of air. So what can we learn from that? And so right now we can see that there's a perfect tornado in there. But what's the problem?
Can't see it.
Can't see it because why? Air is invisible until we put something in it, like, pigs and tractor trailer trucks and grass and dirt.
We have minute tractor trailer trucks just for our audience on Argonne.
However, we're going to be safe, and we're going to do it a different way. So what we're going to do is we're going to produce a cloud. We're actually going to take some dry ice, frozen carbon dioxide is 200 degrees below zero, and it's so cold that when I pull it out of the atmosphere, out of the box right now, you'll see this sort of a smoky, milky sort of smoke around it. It's actually
because dry ice doesn't melt.
It doesn't melt. It actually sublimates. But carbon dioxide is invisible as well. So what it's doing is the cold air from the dry ice is actually condensing the water in the air around the ice. So let's show that. But we're going to first of all put on our personal protective equipment.
Always safety. And while Doug is doing this, I just want to bring you back to say that you are watching Argonne at Lunch. We're talking with Doug Sesterson, who is a research meteorologist at the National Laboratory. We're talking about how scientists model difficult to observe things like tornadoes. So Doug has just introduced the model that he's built. Actually, his daughter Rachel built this model for an 8th grade project. And he's going to tell us a little bit how scientists figure out that what they're observing is actually true by building this type of model.
Okay, so because it's invisible, we can't see it until we put something in there. I'd like to put a cloud in there. So right now I have a piece of dry ice, and you can see it's got this white, wispy, looks like smoke, but actually it's the cold air is coming off the dry ice, and it's actually chilling down the air around it so that it condenses the water vapor into little droplets. And so we've made a mini cloud, sort of how Mother Nature really does it, without dry ice, of course. So what we're going to do is we want to get more than that to see our tornado, so we're going to put it in boiling water. 212 degrees above zero, 200 below zero. It's going to be quite a cloud. So here we go.
Wow.
So it was there all along, but now we get to see it for the first time. So what's happening is that we can actually see what we call the vortex of the tornado. We can see it, and it kind of looks like a real tornado, but what can we learn from this? So the first question we might have, and by the way, we're not doing tornado research here at Argonne. This is really just an analog to show you how scientists would actually use this type of a physical simulation of a tornado to understand what happens in the real environment and be safe. So at this point, if I'm a tornado chaser, I would like to know, well, how close can I get? And the first thought I have is, well, is the wind field just inside the part that I see, or does it extend all around it? What do you think?
I think it extends all the way around it.
Let's find out. So that's what researchers do.
I don't know if I'm right or not. It's just...
So that's why we did the experiment. So what we can do right now is get another piece of dry ice and some boiling water, and we can do streamline analysis. So what I'm going to do is just hold this to one of the sides, and all of a sudden you can see that wow, we're really filling the box. You can start to see that the air is rotating all the way to the edge of the box. Not the part we see, but the entire wind field. The structure all around the tornado actually shows that there's rotation. But if we had a slow speed or a high speed camera in there, we would see that the part that I'm injecting to the side of the box is actually going slower than the middle of the tornado. As a matter of fact, when Rachel did all the calculations, she found out that the wind speed of where I am right now at the edge of the box was 4 times less than the wind speed in the center. So that means if you're a tornado chaser, the part that you see might be 200 miles an hour, but if you come out, and we call this to scale, that if we take one tornado height from cloud base to ground and we come out from it, then we would say the wind speed would be about 1/4 less.
So if we're talking 200 miles in the center,
that's right.
You get about a mile out, you're talking 50 miles.
Yeah,
that's how much the wind is.
That's right. But the point is, it just doesn't go from 0 to 200. There's always some wind present. So we've learned a little bit about this. So let's go see how this really scales to the real thing. So over here we have no signal. What happened to our video? There we go. Just like magic. So this is actually a tornado. It was in Rye, Colorado. And I want to call your attention to the point, here come our storm chasers, they're looking at the column. This would be the center part that we just saw. But the really important part is that there's debris flying well outside of the visible cone. So it's important for, in this type of situation, how close can I get to this without being in danger? Well, even 50 miles an hour with a piece of tin could be fatal, but it's certainly not the same as 200 miles an hour. So they don't want to chase right up to the edge. You really want to hang back, however high it is, tall-wise, stay that distance away, and you'd be about 1/4 of the wind speed. So there's a joke we have, and the joke is that there are old tornado chasers, and there are bold tornado chasers, but there are no old, bold tornado chasers.
And that's the comedy show that we have at Argonne at lunch today. Doug Sesterkin, I love that. All right, so if you're just joining us, this is Argonne at lunch. I've been talking with Douglas Sesterkin. He's a research meteorologist here at Argonne National Laboratory. He just took us through a fabulous demonstration that has to do with tornadoes and how we know, the models that we build accurately represent the phenomena that is difficult to be able to see, like tornadoes. But that's just one part of the equations. Our next conversation is going to be with Rob Jacobs, so I want you to follow me over this way. Rob Jacobs is a computational climate scientist with Argonne, and here he is right now. Hey, Rob, how you doing?
Good, how are you?
All right. So why don't you let me know, give me an idea of what types of projects you work on when here at Argonne.
So here at Argonne, I work on climate models. And what climate models are they're really large computer programs that we write in order to solve the complex equations that describe the climate system and how it works.
And what type of hardware are you using to process all this data? I imagine it's a ton of data.
Yeah, it is. We have to use some of the world's most powerful supercomputers to run these models, and one of the ones we use is Mira, right here at Argonne, which is one of the most powerful computers in the world.
Excellent, excellent. So I see you have an image here. It's a satellite image, actually from 1960. What are we looking at right here?
So, as Doug showed, the atmosphere undergoes all kinds of scales of motion. We have everything from tornadoes to what is called the general circulation, which is a big global circulation. And that's the thing that we have to get right in our climate models. And one of the only ways we have to look at that is through satellites. And this is showing how much the technology has advanced over the years. This is a picture of the first ever image from the very first TV weather satellite. And what it's showing, it's very grainy, it's black and white, it's just one image, and we're looking at clouds. That's what the white stuff is. And we can kind of see through a clear area here. This is the coast of North America. This is the Canadian Maritime Provinces, Hudson Bay, and the east coast of the U.S. is down here.
Wow.
Yeah. Mm-hmm.
How technology has changed. Actually, it looks like the picture from one of my first cell phone cameras. So time has changed. So if so what type of technology? So we're only looking at the visual spectrum here. We can't look beyond the clouds, really. We can't see a lot of detail.
Right. And we have no motion also, which is what's really important in understanding how the atmosphere works.
Okay, so let's talk about evolution. So this is going to be the next one. Now, this looks pretty awesome. Why don't you tell us a little bit about what we're seeing here?
So taking a big leap forward, this is the latest weather satellite that the U.S. has launched. It's called GOES-16. It just started sending pictures this year. It's not yet approved for operation, so this is kind of an early peak. And what this is showing is many, many things. First of all, we have a view of the whole Earth, and we have a view of again, clouds. And we have many images that we can put together and form a movie, basically, of what's going on. This is there's a picture every 15 minutes, and they get stitched together and shown in an animation loop. And from that, we can get an idea of how the atmosphere is moving. And this particular sequence is from the recent hurricanes we had in early September. That's Hurricane Irma that we just saw crashing into Florida there. That's Jose. And Katrina was over here earlier by the coast of Mexico.
Oh, wow. So I'm seeing a lot of information that we didn't see in the previous one. Number one, I'm seeing we have temperature. Now we can find out how hot or cold these masses are.
That's right. This isn't just where the clouds are, but it gives us a sense of how tall they are in the atmosphere. So the taller they are in the atmosphere, the colder they get. And that's what this temperature scale is showing. So these are really high, cold cloud tops. And then down in the bottom, closer to the surface, we have warmer clouds down here. So this gives us something about the 3D structure of the atmosphere.
That's amazing. If you're just joining us, this is Argonne at Lunch. My name is Justin Breaux. Right now I'm talking with Rob Jacob, who is a computational climate scientist here at Argonne. We spoke to Douglas Sesterson earlier. He built an amazing model where we were basically talking about how scientists can build models to help understand difficult to observe phenomena. And we were just talking with Rob about how we just come from an image from the 1960s, and we have a satellite which just put in the air this year, and this is just another way for us to understand the difficult to get at phenomena.
That's right. The atmosphere is, of course, invisible. It's an invisible gas. So we need something in the atmosphere to reflect light and show us how it's moving. Doug was using water vapor, and we're also using water vapor here, only the real water vapor in the atmosphere. Another interesting part of this image that's very important to climate is you can see a little bit of what I call the general circulation. Up here where we are in the mid-latitudes, the air is generally moving from west to east. But down here in the tropics, the air is moving from the opposite direction, from east to west. That's a feature of the general circulation that we need to get right in our model.
Is that also why toilets in Australia flow backwards?
No.
No. No.
Partly.
All right, so this is amazing, but now we have more of a model that is based more on theory, and I think that's the next image that we're going to see.
That's right. Now we have all this information from our satellite. Can we capture that in our model that runs on this? And this is an image from one of those models. So this is no particular year. This is a purely theoretical calculation of the general circulation of the atmosphere. And we're looking at, and because it's a computer model, and we just have numbers that come out, we can use computer graphics techniques to show us whatever image we want. We don't have to rely on having water vapor to show us what the atmosphere is doing. So in this case, we took all of the, not just the visible clouds, we took all of the water vapor into the large, that's a very wet part of the atmosphere. This is showing.
Pick up my questions here. Oh, thank you very much. All right, so what we're going to do now is I have another couple of questions for you. So is this just how have advances in knowledge about weather systems created changes in scenery?
So, as we've learned more about the global weather system, that has really helped us especially satellites are able to show us hurricanes that didn't exist. So looking for satellites that have an atmosphere and the hurricanes occur. That's another good statistic.
Another thing that I'd read when we were researching about this, I heard about this word couple. I guess that has to do with you have these models and they have to talk to each other because they're models of different things within the atmosphere. Talk to me a little bit about how you allow different models to talk to each other to produce something.
Sure. So this is a giant computer program that produced this image. And inside that program, a separate program for the atmosphere, another one for describing the ocean, and we have another one even for describing how the landscape is. So all of those models, in order to simulate the climate, have to be able to talk to each other. And that's what we call coupling. We like something like the ocean, but the air has to be able to feel that. So the coupler makes sure that the warmth of the ocean produces a heat flux into the atmosphere to warm it up.
That's amazing. That's amazing. So what I want to do is bring Doug back in here. We have a few questions that were asked before. So, and I'm going to let you guys decide on who's going to answer it. So, where do you obtain your data?
I could talk more about Rob, where he gets his data, actually, because today
the climate system will take data wherever we can get it, because we need to understand how everything is moving from the bottom of the ocean to the top of the atmosphere. So we need not just satellite data, but we need shipboard temperature observations from drop zones that go through the atmosphere, things they throw overboard into the ocean to measure the depth of the ocean.
about weather balloons on a daily basis.
So weather services launches weather balloons.
Question. You need data from the cooler. What do you mean by model? So we've been talking about model, but if you want to give me another example, when people say model, you think about model trains. It simulates something. So if you want to go a little bit further and explain what model is.
I think we give you two examples of models today. So it's a physical model. In this particular case, tornadoes just don't stand still, and we can't put it in a laboratory and study. So I have to make something downsized, small enough that replicates what a tornado does. So put it on a bench and study it. So you can have a physical model of the representation of the physical thing in the atmosphere. That's one
So mathematical physical model. Behind those are equations like the second law of motion, written down to describe the motion of a fluid gaseous that goes through the atmosphere and lines up the atmosphere. Equations for property information. So all of those equations are then converted into algorithms. The algorithms are converted into computer code, and then we run that code on the computer to solve the equations and get these kind of functions.
The current job with climate research. And so we're part of the National Research Facility where it's interesting. We go by competitive bid to take tractor trailer trucks of basically weather instruments to places of the world where researchers want to go and get data that's missing. So ironically, it's if we go to where the models seem to agree. And the whole idea is that even though we have a model, we use the data to get a model to understand the process that Rob was talking about, but we also use the observations to validate that the model produces as a forecast.
Next question. What is carbon-13? What's that got to do with climate?
I got that. So, boy, that's a good question. You did your homework. So, basically, there's several isotopes of carbon. Carbon-14 is what we've been dating with. Carbon-13 is the most prevalent. Carbon-12 is actually unique to plants. Now, when we talk about global warming, we talk about greenhouse gases, primarily carbon dioxide from the burning of fossil fuels, that's adding to the greenhouse gases that trap the heat in the atmosphere, which is causing global warming and climate change. So what's really important is how do we know it's us? How do we know it's not some other natural phenomenon? Well, carbon-12 is unique to plants. And when plants die and become a goopy mess called oil and we burn it, guess what? It's carbon dioxide, but the carbon is carbon-12. Same thing when we burn coal. But the atmosphere mostly has carbon-13. So we can look at the ratio of carbon-12 to carbon-13 over a long period of time, and we find that actually tracks to global temperature.
Thank you, whoever asked that question. That's a beautiful. I didn't know, and now we know. Good. Other than the public, are there industries that rely on weather data?
Many industries are represented. Agriculture, of course, is a big one. A lot of tourism, entertainment industries depend on having good weather. So it's a hugely important part of the economy.
Last question. What type of software do you use to model climate? We talked a little bit about that, but basically we use supercomputers, but if you want to go a little bit further into it.
So yeah, all the software is custom written. So there are no off-the-shelf commercial packages that we can use to model the climate system. There's a lot of commercial packages that do fluid dynamics that you can purchase, and some of them are free. But that's mostly for fluid flow and small particles and other kinds of laboratories. So they're not for modeling the fluid of the atmosphere. So these are all custom written in computer languages like Fortran.
And you write these yourself? I mean, there's a...
Okay. I got it at a desk and typing it all up.
All right, I want to thank you for joining Argonne at Lunch. I've been joined by Doug Sesterson, he's a research meteorologist here at Argonne, and Rob Jacobs, who is a computational climate scientist. I'm Justin Breaux. We'll see you next time. Thank you so much.